Okay, so we are getting started. Other colleagues will find us. Good evening to you all.
Yes.
Can you hear me well?
Yes.
What did we look at last time? What did we handle in job 1?
You hate me.
Hello members, what did we handle in? Come again? Okay, we looked at theories to justify continental drift. So today we are continuing with the theories. We looked at Wegener's theory, and today we want to continue and look at the plate tectonic theory. Isn't it? I'm going to mute all of you so that we are able to hear from one another. Can you see my screen? Can you see my screen?
Yes.
Okay. So let's first see this small video. From there, we can get started. Plate tectonic theory. Is my screen seen?
Yes.
Okay.
Take a look at the outer surface of our planet. It may look like one solid shell. But according to the theory of plate tectonics, this outer layer, called the lithosphere, is actually broken up into massive, rigid slabs called tectonic plates that fit together like puzzle pieces. Floating on a thick, molten layer of the mantle called the asthenosphere, the plates slide around like slow-motion bumper cars, traveling up to 6 inches a year. Right now, Earth's crust is divided into 7 large plates and dozens of smaller ones. The boundaries between these plates are dynamic and violent places that make and break Earth's crust. The relative movement of the plates creates 3 types of boundaries. A divergent boundary occurs when 2 plates move away from each other. On land, you can easily see this. Diverging plates create huge troughs, like the Great Rift Valley in Africa. If the spreading here continues, the Indian Ocean will eventually flood the rift, converting the entire eastern Horn of Africa into a massive island. Transform boundaries are where 2 plates grind past each other in opposite directions. The most famous example is the San Andreas Fault, where portions of Southern California, including Los Angeles, are sliding roughly 2 inches closer to Northern California each year. A convergent boundary, on the other hand, is where 2 plates collide. The impact often weakens and crumples the crust upward into jagged mountain ranges.
Okay. Are you there? Can you see my screen? Hello? Can you see my screen?
Yes.
Frank, can you see my screen?
Yes.
Okay.
Yes.
So that was the introduction about plate tectonics theory. What have you seen from that video? Raise up your hand. Hello. Yes, proceed. Proceed, we can't hear you. David Katete, what have you seen in the video?
What we have seen in the video is that the outer surface of the Earth is divided into blocks, which are known as tectonic plates. They are divided in their divergent tectonic plates, and they exist in areas which are violent. And okay, basically that's what I've gotten from the video. It was short. I think that's what I got.
It was short, but almost explaining what we are going to study. Arvin.
What I've been able to get from the video was that like the plates are in a constant motion, and the rate value to maintain the split in the ocean we talk about space.
Okay. Okay, that was good. Someone else to read the slide here. Someone to read. We need to be quick and summarize this theory. Members, we are too quiet. Can I say the video made it all? We can go. Yes, Louisa.
The theory of plate tectonics was put forward in the 1960s. It coincided with a time when a large amount of research was being conducted about the ocean floors. Since then, better understanding and technology has refined the theory to explain how the Earth has been shaped. Plate tectonic theory involves processes to which parts of the Earth's crust break up and slide horizontally on top of molten rocks of the upper mantle.
Thank you. Continue here. Continue.
The theory assumes that the Earth crust is not in one piece, but is divided into a number of separate parts called tectonic plates. These plates are mobile, floating on the partially molten rocks of upper mantle. The lighter continental seal rocks rest on top of mobile tectonic plates. There are 6 main plates and about 12 minor ones, but the important regions are the boundaries where plates meet or move apart. Major plates are Pacific, the African, the Indian or Australian, the Eurasian, the North and South American, and Antarctica plates.
Thank you. So members, we need to understand that the theory must be stated the way it is. And so now we are looking at plate tectonic theory, trying to see the theory that explains the distribution of continents and ocean basins, how they came into existence. And now we are looking at their distribution by the plate tectonic theory. So here we are looking at the plate tectonic theory involves processes to which parts of the Earth crust break up, they move horizontally on top of the molten rocks of the upper mantle. Now, in the other video, you saw the divergent, and then we shall also see other forces as we continue. So here we are now looking at that these plates are mobile, they are floating. They keep floating on top of molten rocks. They keep floating. So because the continental or the shear rocks rest on top of tectonic plates. And these tectonic plates, whenever we talk of a plate, we are basically looking at these ones. We talk about the 6 main ones. Those are the bigger continents now. And then the 12 minor ones. So if we can talk of the Australian plate, you know, Australia is not something big. So those are the minor ones. And then the 6 main ones, if you can talk of Africa as a plate, you talk of North America as a plate. So we have bigger plates and then the 12 minor ones, also call them plates. So look at that. Here we are looking at those bigger plates, North America, South America, Africa, Eurasian plate, talk of the Indian plate, Antarctica plate. Those are the bigger plates you can mention. And then other minor ones. Look at that, look at that. So those are different plates. This diagram is very important when you are describing the plate tectonic theory. You need to include different plates and at best different forces, especially those boundaries, the transform. We shall look at others that are really parallel. Then someone else take on this slide. Someone else? Raise your hand. I'm going to pick Madrid, unmute.
Horizontal movements take place due to internal forces, that is geochemical, geophysical, and radioactivity reactions generate heat that melts rocks, giving rise to convection currents that drive the plates. Plates change over time in terms of position, size, and shape. As plates move, continents on top also move following the direction of plate movements. Plates margins are seismologically active, creating 3 types of margins or boundaries, i.e. constructive margins or divergent boundaries, destructive margins or convert boundaries, and neutral or
Conservative margins.
Or transform boundaries.
Okay, thank you. Continue. So here we are showing different types of margins. Divergent, they are taking to different directions. Convergent, they are bringing into the same direction. And then transform, they are parallel. Can you see those diagrams well? Yes?
Yes.
Okay, so those are different boundaries we are looking at, or those forces that make plates move because they will take in different directions. Once the divergent margins work on the plates, they have to move in different directions. If the convergent boundaries or margins work on the plate, it will bring something to do with mountain folding. And then the transform, these ones move parallel. And we can, as the other diagram was showing, we saw different mountain ranges having different heights and the cracks in them. Someone else to continue from there. I'm going to pick Mulondo. Unmute. Mulondo, are you there? Arvin? Speak loud.
The plate tectonic theory, the movement of tectonic plates results in the movement of continents and land masses. Continents, land masses, and water bodies change their positions relative to each other. All the continental land masses and oceanic and oceans are moving closer to the North Pole and closer to the North Pole. The Indian and Australian plates are moving northeastwards. The Pacific plate drifting northwards, as well as the North American land masses. The South American land masses moving westwards. There are three types of plate movements or boundaries caused by convection of currents which influence the distribution of continents. These are divergent movements caused by tectonic plates moving from one another. This lead to faulting and wrapping of crustal land masses on the seafloor. This spreading process produces mid-ocean ridges and islands. For example, the mid-Atlantic ridge is a divergent plate boundary where the seafloor spreading occurs. Iceland sits atop a divergent plate boundary where continental rifting occurs. Convergent movement is caused by tectonic plates moving towards one another, and as a result, continental land masses may move towards each other, getting closer. Collision may occur, leading to the folding and formation of fold mountains, e.g. the Himalayas, due to the collision of India and Asia.
Thank you, Arvin. So here we are now looking at those plate boundaries. And in these plate boundaries, we are basically explaining these ones, that when divergent margins happen, what is the result? When convergent margins happen, what is the result? When transform boundaries happen, what is the result? So we started it by saying that now, when you look at that the movement of tectonic plates results into the movement of continents or the land masses, and thus water bodies change their positions relative to each other. And now all continental land masses and oceans are moving closer to the North Pole. You find that the Indian or the Australian plates are moving northeastwards. The Pacific plate is drifting northwards. And then North American landmass also is moving northwards. The South American landmass is also moving westwards. So all of them are always moving closer to the North Pole in their respective directions. Then we are looking at the cause of these boundaries, or it is because of the convective currents, and these convective currents, they are the boundaries. When divergent movements occur, we shall see that the sea floor, you will find that when these divergent forces happen, the sea floor now is going to produce mid-ocean regions. For example, those ones that are seen in the mid-Atlantic ridge or in the mid-Atlantic Ocean. Then we find that because of divergent movement, Iceland sits on top of a divergent plate. Here, the plate tectonic theory is giving different forces, or call them convective currents, and evidences where it has appeared. In the chart, Patricia is saying, Ivan, Victor, Kasule, Murondo, Maureen, you share your contacts. You haven't shared your contacts. Please put your names and contact in the chat. Okay, we continue to see that when convergent movements happen, tectonic plates are moving towards each other. And so when they happen close to each other, we shall find that there is collision. And so folding will occur. Thus, fold mountains appear. For example, the Himalayas that are found in India and Australia. The Himalaya mountains, we shall look at them. You need to remind me. Then, when continents move towards oceanic plates, they cause subduction. This is because they are denser cymatic rocks. So collision of plates and subduction leads to formation of trenches. Best examples are located in Nazak, Java, and Tonga trenches. Then oceanic crust may move towards each other, causing narrowing of ocean basins, and continents move nearer, leading to formation of trenches and volcanic arcs, e.g. Pacific Eurasian plates led to Mariana Trench and Japan arc. So all these different currents, they bring up different features as stated in the tectonic theory. Someone else take over this. Still I choose Frank, unmute and speak. Speak and be loud.
Transfer movement, where plates move past each other, hence no collision or diversion. They offset sections of continents, ridges, and trenches, e.g. North American plate moved against Pacific plate, forming San Andreas fault in California, causing offsetting of land to the west. When fracture near the Gulf of Aden and Romash fracture offset West Africa. NB, lateral earth movements are or large-scale differential movements that operate horizontally within the Earth's crust. They are caused by internal forces or divergent forces, where resulting strain and stresses in the rocks. They lead to folding and faulting of the crust.
Okay, thank you. Though your network was up and down. But so here we are looking at the transform plate boundaries. So the transform, these ones we say that these ones move past each other. Let's say that one is taking in that direction and this one is taking in that direction. So when you have such forces or margins, these ones, they offset sections of continents, and thus they will lead to formation of ridges and trenches. Best examples are seen North American plate, which moved against the Pacific plate, forming the San Andreas fault, which is located in California. And then we also have Owen fracture. It is found near Gulf of Aden, and then Romanchi fracture off the West African coast. So this is where you can find this, and these were brought about by the transform movements or transform margins or transform boundaries. So when we try to explain the lateral earth movements, we say that they are diastrophic or they are large scale differential movements that operate horizontally. Because basically we have seen that plate tectonic movements, we are looking at horizontal forces that are acting on plates because they are mobile. They are caused by internal forces, call them the divergent forces, resulting into strains and stresses on the rocks, thus leading to folding and faulting. So tectonic plates basically deals with those features that were as a result of folding and faulting. We continue. Okay. Someone to read about vertical earth movements. Yes, I pick who? Proceed. Unmute and speak. Let me pick Lamla. Lamla. Unmute and speak.
Teacher, I've just joined.
You have just joined. Then read for us this slide.
The plate tectonics theory. Vertical earth movements are diastrophic movements that operate vertically, exerting pushing force onto the crust either upward or downward along a radius from the center of the earth to the surface. They usually occur on a large scale, hence called a pyrogenic, in brackets low, large scale uplift, and may involve vertical uplift or subsidence, possibly the result of isostatic readjustment or warping at tilting. Maybe on a local scale, especially around the coast, thus affecting the relative level of the land and sea, and therefore the nature of the coastline also lead to warping and tilting.
Okay, thank you for taking us through that slide. So we have, first of all, we looked at different forces. We looked at those ones which come to same direction. We looked at those ones that are pulling apart. We looked at those ones that move past each other. All those ones are lateral. Now we are looking at vertical. Please mute. When we are looking at the vertical, if this is the earth and our center is there, these ones, they are now moving vertically like that or like that. Those are the forces, vertical movements. Members, are we together?
Yes.
Okay, so we have said that these forces here, they can lead to folding. These ones can lead to creation of trenches. These ones also can lead to creation of trenches, arcs, and the rest. Then these ones, because they are moving vertically in that nature, they will lead to warping, they will lead to tilting because they are vertical in nature. More to that, let me see if we have more text to read. We need to wrap up this by clearly observing this video. You note what you have missed in this video. Note down what you have missed and what you may need to ask. Watch very well.
Everyone, I figured I'd throw together a quick video just to review some of the content you've been working on in class. Let's get started. Obviously, you've been working on...
Can you see my screen?
Yes.
Yes.
Okay. So that members don't unmute themselves, let me mute and you listen carefully.
on this theory called plate tectonics, which is basically an extension of Alfred Wegener's work. This theory that we're going to look at was put together in the mid-1900s and built upon what Wegener began working early in the century. So let's get started. The first thing we need to know is this. The outer shell of the Earth, which I gave an example of being the magic shell on a scoop of ice cream, this solid outer crust of the Earth, we call it the lithosphere. It's actually broken into pieces that we call plates. You see them here. You can call them lithospheric plates, you can call them tectonic plates, or simply plates. But this is the solid outer part of the Earth that we live on. Some of the plates are all oceanic crust, some of them are all continental, and some are a combination of the two. That's going to become important. Keep in mind that we do have these two distinct types of crust. If you look at the gray here, this is our continental crust. It's thick, it's made of the rock granite, it's not quite that dense, only about 2.7 grams per cubic centimeter. But if you look at the dark gray area under the oceans, that's the oceanic crust. It's very different. It's much thinner, more dense because it's made of the rock basalt. The density of the basalt is about 3 grams per cubic centimeter. Keep in mind that information can be found on your Earth's interior chart in your reference tables. Now, that crust, whether it's oceanic or continental, along with this kind of orangey section called the rigid mantle, those two together are what make up our lithosphere, this solid outer shell of the Earth. Keep in mind that beneath that is kind of a gooey, plastic, partially melted bubblegum layer called the asthenosphere. And so the plates that we live on are actually floating on the asthenosphere beneath. Now down in the asthenosphere, that melty, gooey, bubblegum-like rock is actually able to move. And it moves because of a process known as convection. Essentially, convection says that hot material becomes less dense and rises. And then when it rises, it cools down, becomes more dense, and sinks. And what we end up with are these rising and sinking currents called convection cells in the mantle. Those end up being the machine, the force that is driving the motion of the plates. So in this diagram, we have a type of boundary called a divergent boundary where the plates are literally being ripped apart by the movement of the convection beneath. Keep in mind, this convection takes place in the asthenosphere, right below the lithosphere. So let's take a look at a map of the plates. Okay, there's a very similar map in your reference table, which we'll see shortly. But for the moment, take a look. You notice that the plates, some are very large, some are a little bit smaller, but they're all moving. And what that means is that there's lots of action at the places where plates meet. For example, that's where we find all our earthquakes, shown here with pink dots. That's where we find all our volcanoes, shown here with red triangles. And this is also where we find a lot of the Earth's active mountain ranges. So keep in mind that all seismic activity, earthquakes, volcanoes, and mountains, tends to happen at or near these boundaries between plates. Which brings us to those boundaries themselves. Now, all of plate tectonics comes down to the fact that things happen when two plates interact with one another. So we need to know what those interactions look like. And it really boils down to 3 types of interactions, 3 types of plate boundaries. The first is known as a transform boundary, and that occurs when plates slide past one another, as seen by these arrows. We also have convergent boundaries where plates collide, and divergent boundaries where they drift apart. You should be familiar with each of these and the kinds of things we see at each of them. So let's go into some examples here. Okay, I'm going to be alluding back to this chart. This is a map in your reference tables that shows plate boundaries. So keep that handy as you're continuing to learn about this. Let's start with transform boundaries. So these are the boundaries where plates slide past one another. If you take a look at this animation, you'll notice the lithosphere floating on top of the asthenosphere is being driven by convection currents, which is causing them to slide laterally past each other, right past each other. And so right along that boundary in the middle, you get a lot of pressure built up, a lot of grinding of the plates, which is often released in the form of earthquakes. Transform boundaries very commonly have earthquakes. However, they don't tend to have volcanoes, they don't tend to have major mountain ranges, and certainly not trenches. The only real feature we see at transform boundaries are earthquakes. This is an example of a place on Earth where you can actually see a transform boundary at the surface. This is known as the San Andreas Fault, and it's found in California. It's responsible for the big earthquake risk of cities like San Francisco and LA. Let's go back to our reference table for a minute here and see that the transform boundaries are shown down on the bottom with this symbol, shown in green here. There's a couple of them, not too many, but the most famous and important one would be the San Andreas Fault, shown right there. Again, if you forget how transform boundaries actually work, the arrows kind of reveal the motion, so it's a good tool to use your reference tables. Next type of plate boundary would be convergent boundaries. Now, these are a little more tricky because we have to consider not only the fact that two plates are coming together and colliding, but what type of crust is involved. For example, we see different things happening when it's oceanic crust colliding with oceanic crust, as opposed to when it's continental colliding with continental, and so forth. And so we have a few different types of convergent boundaries. The first type we call a subduction zone, and as you can tell by this little animation here, this happens when continental crust on the left collides with oceanic crust on the right. Now notice that the oceanic crust is sinking underneath the continental crust, and that's because oceanic crust is more dense than continental crust. It's heavier. And so when the two collide, the heavier oceanic crust sinks underneath the lighter continental crust. When it sinks, it melts because it's hot down in the asthenosphere. And that melting rock finds little cracks and crevices to rise through and ultimately erupts at the surface, forming active volcanoes. So some of the features we look for at subduction zones are a chain of tall mountains and active volcanoes, a deep ocean trench seen by this dark line just off the coast, as well as lots and lots of earthquakes which tend to happen along that subducting plate. We also have island arcs. Now, very, very similar to a subduction zone. The only difference is that this is oceanic to oceanic, so no continents involved here. The one thing that's tricky is it's a little hard to tell which plate is going to subduct, being that they both have the same density. But eventually one plate, usually the older rock, will sink under the younger rock. And again, we will get this melting, which causes rising magma to create active volcanoes, which in this case form islands, volcanic islands, because we're talking about areas out in the middle of the ocean here. We also get a trench, which you can see clearly in the water there. And of course, we get lots of active earthquakes along the subducting plate. Before I go back to the chart here, we also have a third type of convergent boundary called a collision zone, and that would be continental to continental. The best example of that would be India crashing into the Eurasian plate, where the Himalayas are forming. But again, convergent boundaries can be seen with this symbol down here, and probably the most famous one that we will discuss is the Peru-Chile Trench on the west coast of South America. So that would be an example of a subduction zone, because you notice the Nazca Plate is in the ocean, so that's oceanic crust. The South American plate is a continent, that's continental crust, and so that gives us a subduction zone. That's where the Andes Mountains are, lots of volcanoes, lots of earthquakes. Finally, we have divergent boundaries where different plates drift away from each other. Again, we want to consider the type of crust involved. So if it happens on land, we have what's called a rift zone where the land actually rips apart into two. We see this happening in Eastern Africa right now at an area known as the East African Rift Zone. As you can imagine, when the rock rips apart, it allows magma to escape. So we get active volcanoes. We do get some minor earthquakes here, though they're not as significant as the convergent boundaries would be. Often we will see this out in the middle of the ocean, and we call that a mid-ocean ridge, shown here. So the convection currents are actually pulling the plates apart. The magma is coming up in the middle, forming mountains and volcanoes, and again, some earthquakes. Now, there's one tricky thing of this, or actually a couple tricky kind of points here. One is not too bad, and that's the idea that the younger rock is always going to be found right along the ridge, because that's where all this magma is cooling to form new rock. As you get further away from the ridge, the rock age will increase. It gets older and older and older as you get further from the ridge. Now, here's the trickier thing. This rock, when it forms, it actually records the Earth's magnetism. If you recall, we talked about how the Earth is like a giant magnet. But that magnetism changes every so often. And so those changes are recorded in the rock. And so what we see in the rock on either side of a mid-ocean ridge are these alternating bands of magnetism which match up on either side. And that's an important observation because it proves that the rock is actually spreading apart, and it proves that the divergence is actually taking place. So if we look at a reference table, here's the symbol for divergent boundaries. And again, the most common one is probably the one that spans the Atlantic Ocean, the Mid-Atlantic Ridge right through here. It actually extends all the way down south, but that's probably the best example, although you see them all throughout the oceans of the world. Now, we do have one problem here because plate tectonics says that all volcanoes and earthquakes should happen at these plate boundaries. But if you really look at the Earth carefully, there's a handful of places where we get volcanoes that are not at a plate boundary. And the best example I could give would be Hawaii, smack in the middle of the Pacific Plate. And so geologists had to consider this and come up with an explanation as to why we had some volcanoes that weren't at plate boundaries. And the answer is that these locations are hotspots. So a hotspot is simply an area where we have a single area of magma that's able to punch through in the middle of a plate. So we're not talking about a boundary here. We're talking about one simple individual solitary point where you have active magma rising up, and it rises from something called a plume. We can't predict where these will happen. We notice there's maybe a dozen of them on Earth right now. Sometimes they're very active, sometimes they're not as active. Here's how they work. If you look at this diagram, you're going to notice shortly a mantle plume, there it is, coming up from the asthenosphere. It's just a hot spot. And that magma is strong enough to actually punch through the lithosphere to create an active volcano. But the problem is the lithosphere is moving, because remember, all the plates are constantly moving around. And so you'll get this active volcano, which is then dragged to the side, making way for a new active volcano to form. And then that is dragged to the side, and a new one will form, and so forth. And so what you end up with is this chain of islands, if it's happening in the ocean, with one active volcano over the hotspot, and then a chain of extinct or dormant, not active volcanoes extending away from it. And what's cool about this is if you look at where the extinct volcanoes are, they tell you the direction that the plate is moving. So that's pretty much in a nutshell the content that we need to know about for this chapter. You guys will be learning a lot more about it in class coming up, but I just wanted to do a quick overview for you. Thanks a lot.
Okay, hopefully we have summarized the entire theory of plate tectonics. I'm going to share notes. I'm going to share these slides in your WhatsApp group. I'm going to attach a question there so that we are good to go. Is that okay? Okay.
Yes.
So for those who would like to continue with our system, remember our free classes are ending tomorrow. So in case you want to continue, those of us who have been craving and crying for a monthly package, we have put a monthly package. So you can pay for 100,000, you continue learning. This is paid once. And so, but if you find that, let's say the lockdown continues and you want to study for 12 months, that means that you will have paid 1.2. And someone who pays 500 is better because you will study for all the 12 months. Those are 365 days. So someone who pays 500 is better than someone paying 100 every month. So you need to see the advantage and pay for the package that you need. So other services, you can only read content, 20,000. You can only, this is at 1 month. For 3 months, 50,000. 6 months, 70,000. And the whole year at 100,000. Only content access, no teacher is involved. Where you need a teacher, you pay 500,000 for a full year, 100,000 monthly. Techno F1, you have your hand up. Can you speak? Unmute and speak.
I was like, where should we pay that money from? Which numbers should we use?
When you check in the group, we have communicated all the numbers. We have put a bank account. We have put a mobile money number. Use any of the numbers. Okay?
Okay. Yeah.
Read that long message we have put in the WhatsApp group. You read it and understand it very well. You won't have many questions.
Yeah.
You can as well simply buy subjects or subjects for your combination at 50,000. If you want one subject, 10,000. So use those numbers, send money. After sending, you talk to me, then I do the needful.
It's okay.